I think the first step to maximize the output power of your panel is to not put it in the shade, but there are some applications where you have to. So it all begins with an idea, with a concept. Usually we sit together and we brainstorm, okay, we want to build something that does this and has these characteristics. We think of concepts and what kind of features we should include. And then what we do is we start simulations.
Basically, what we looked into is how can we improve this operation of solar panels if they are partially shaded. And basically then the point is that we still want to use part of that partially shaded part and not just cut it out of the power production, but still be able to use that part to whatever extent it's shaded or not.
So we are taking part in this project collaborating with Yacht Zero. They are trying to show that you can run the entire yacht based on renewable energies. There are some challenges that come with that. One is that when you're in anchor and the wind is not blowing to charge your batteries, you're solely reliant on solar generation. Therefore, it's very important to draw as much power as possible from the solar panels.
So I think in general, next to this very specific application where this development now was started for, the much more general use case of this would be in building integrated solar panels, where basically it goes beyond just putting solar panels on the roof, but really on the facades, and where you have way more shading because of other buildings or light poles in front of the building.
My name is Lucas Irazusta, and I'm working at DC Opportunities as an electrical engineer.
I'm Lawrence Mackay. I'm the founder of DC Opportunities, and at DC Opportunities we develop the next generation technology for DC microgrid and DC distribution grids.
And we are Foundation Zero, a platform that promotes the use of renewable energy by openly sharing insights and data from a range of innovative engineering projects like this one, which set out to solve the curious problem of how to maximize the efficiency of solar panels when they are placed in partial shade.
Solar panels consist of a series of cells which are connected in series among them. That means they are sharing the same current. It happens to a solar panel when it's shaded. Even if one cell is shaded, the current of the entire panel, and therefore the power output, decreases significantly. A good analogy is to think of a gardening hose that you pinch in one spot, and even though only one spot is pinched, the water flow of the entire garden hose is affected by it.
So the traditional solution for this problem is that panel manufacturers, they place 3 bypass diodes in the panel to split the panel into 3 sections, and then in that way, if there's one of those thirds is covered, so you can just bypass that whole section, and then you lose just 1/3 of the panel and still can use the 2 other thirds of the panel. The challenge is that you still use that whole third of the panel, and even though you only cover one cell of that third.
Usually what you will find in industry is that you have several of these panels on a solar park, for example, and they are all installed next to each other. And then what you will have is an inverter connected to an array of solar panels. So let's say, for example, 20 of these. The problem in those installations is if one of the panels is shaded, this affects the output power of the entire string because they all go to the same inverter. Now, if you try to make it more localized and have a higher resolution, what you can do is install an inverter per panel, for example. So then the behavior of each panel is unaffected by the rest of the panels. Following that thought and pushing it even further, what we are experimenting here is to divide the panel into several strings and treat each string independently. So that if one string, for example this one, is shaded, we can adjust its operating point accordingly, and the rest of the panel can keep operating at maximum power. The way our system is set up is it consists of 2 conversion stages. The first converter is responsible for performing maximum power point tracking, and that means extracting as much power as possible from the cell string. So as we said, in this prototype we have 6 cell strings. And what we do is we have one MPPT converter connected to each of the strings. Then you can perform MPPT at the string level, basically. So if one is shaded, it can adjust its operating point to allow the rest to continue operating at maximum power point. The grid configuration we have here is a bipolar DC grid. So that requires a second conversion stage, which is what we call the isolated converter. And what this does is it takes the power generated from the first stage, which is the MPPT, and steps it up to couple to the bipolar DC grid.
So due to the wider voltage variation per panel that we get because of the maximum power point tracking, we need to have a converter that's able to handle a very big voltage variation. And typically what happens with converters that have to operate at a very big voltage range is that they are less efficient.
So we have incorporated many cool technological features in this second converter. These include planar transformers, gallium nitride switches. We are using advanced software control. We base the entire controlling on Drup. The topology of the converter is based on topology morphing, which means we have incorporated 3 different topologies in one converter.
A full technical breakdown of this solution is detailed in the team's research paper, which was presented at the International Conference on DC Microgrids. And that leads us to the next interesting part about this project, which is the bipolar DC microgrid, which the panel was designed to integrate into. Why DC, you might ask? Good question.
Once upon a time, when the western part of the world was electrified, the war of currents occurred between Edison and Tesla. And the question back then was, should we have AC or DC technology to bring electricity? And long story short, back in the day, the decision was to go with AC. The reason being is that when you are transmitting the current through long distances, you want to have high voltage to have less power losses. But when you bring it to a household, you need to bring that voltage down to power your load. So in order to convert those voltage levels, back then they had transformers, and that was the best suited solution. Things changed in the 1960s with the introduction and the popularization of semiconductors. That's a technology that allows DC conversion in a very efficient and compact manner. And nowadays it's possible to have power electronics and change voltage levels also in DC.
So the main advantage of operating things in DC is that we can get rid of all the conversions in between. That has different benefits. A big one is that you don't need a converter. If you don't have that converter, you don't have to pay for it, you don't need to use the materials, but also if you don't have it, it cannot fail. So you can increase the reliability. Then if you don't have the converter, you don't need the space for it as well. And also don't have the losses of these conversions. There's additional benefits that we are also especially looking into is that it becomes easier to make a robust power system because it's just very clear based on the voltage. If the voltage goes down, then you know we have too little power. If the voltage goes up, we have sufficient power. And based on that, we can make a very robust control system that makes it also much easier to have very decentralized systems that can even continue operation if big things go wrong in our power system.
Now that you understand to some of the nuances of the relationship between renewable energy sources and DC microgrids, it's time to dive into the results.
So what we did was we installed our converter on a solar panel which was divided into 6. We brought it out in the sun here. What we did was we placed it in front of a tree, then the tree would cast a vertical shadow on the panel, and then throughout the day this shadow would be moving. And the most important part is we compared how much power we were generating at each given time compared to what we would have generated if we didn't do cell string level MPPT conversion. We saw results that showed that we were withdrawing up to 3 times more power than in a conventional panel. The limitations of this is that it's heavily dependent on how the shadow is casted. If it's only shading one string, then that's a best case scenario for us to show the potential. If it's shading more than one string, or all of them, then the output power unavoidably just goes down.
Although this experiment didn't end up making it out of the lab and onto Yacht Zero, it's a solid proof of concept for further development in this niche area.
I think one of the very interesting things within this project was to really think into these details on how we can really make a really efficient and good system. I found it always interesting again to explore new issues. For example, we had when we were designing the small micro maximum power point tracking converter, we realized that our current sensor that we were initially thinking of maybe using would have more losses than the whole converter itself. So we came up with a new solution how we could eliminate all these current sensors in the micro maximum power point tracking. Within this project we really had the possibility to explore these kind of new options, also like with this like topology morphing converters, to really explore what are the limits of what is possible in order to get efficiency out of solar panels.
Our team specializes in research and development of new technology. It's very important to find the right people to collaborate with, because in big companies or in industry, they often don't want to change too many things. If things are working, then why change it? But then you get stuck and you actually miss out on the newest improvements, and you actually don't achieve the full potential the technology could. So it was very interesting and very nice to collaborate with Yacht Zero, because they're willing to take risks and they want to push the limits and see what's out there.